Hello everybody. In this video we'll be going over one of the sections in chapter 6 of our text entitled Chemical Composition. In this video we're going to discuss how we can use chemical formulas as conversion factors. So let's start off by thinking about how we count the number of parts we have if we know the number of holes that we have. Okay, so if we know how many parts are in the hole unit, by counting the number of hole units, we can effectively also count the number of parts. Right, so a simple example of this is that if all the desks in the room have 4 legs, and there are 30 desks in the rooms, there are going to be 4 times 30, 120 legs. Since every H2O molecule has 2 hydrogen atoms in 100 molecules, there are going to be 200 hydrogen atoms. Okay, so we can extend the logic we have simply when we're trying to think about how many parts to order, say, for our desks, to the number of atoms that are inside the molecules. And this logic even extends to moles. So in 1 mole of water molecules, there are 2 moles of hydrogen atoms. Since we count atoms and molecules in mole units, it makes sense that we're going to want to find the number of moles of the constituent elements if we know the moles of the compound. So because we're going to be calculating the number of moles of everything, because that is our gateway between atoms and mass, this is our useful unit, it makes sense that we're going to want to figure out the moles of the constituents. So if there's 1 sodium and 1 chlorine, for instance, in an NaCl, 1 mole of NaCl is going to contain 1 mole of sodium and 1 mole of chlorine. If we have something a little bit more complicated, like our calcium carbonate here, we can see that 1 mole of calcium carbonate is going to be 1 mole of calcium, 1 mole of carbon, and 3 moles of oxygen. Remember that we're using our subscripts to figure out how many atoms there are in a molecule, and now we can use it to figure out how many moles there are in a mole of this compound. Let's try a problem here. See if we can calculate the moles of oxygen in 1.7 moles of calcium carbonate. Okay, so we've seen it for 1 mole. Let's see what happens when we make it in odd number of moles. We're given that we have 1.7 moles of calcium carbonate, and we're asked to find the moles of oxygen. Our solution map is moles of calcium carbonate to moles of oxygen. So the fact that we need is how many moles of oxygen there are for every 1 mole of calcium carbonate. We've seen now that there's 3 moles of oxygen for every 1 mole of calcium carbonate. And now we see that we want to cancel the moles of calcium carbonate and get out moles of oxygen. Notice that when I wrote these conversion factors in this statement, I did label the moles with which thing I'm talking about. Okay? This is very useful, even though it's only a label, in order to keep it straight what exactly we're talking about. Don't want to get confused by just writing out the mole unit and then forgetting which moles you're talking about. If we apply our conversion factor, we see that there's 1.7 moles of calcium carbonate, 3 moles for every 1 mole of calcium carbonate. We can cancel those moles of calcium carbonate, and we see that there's 3 times as much, 5.1 moles of oxygen for every 1 mole of calcium carbonate. Don't let the fact that there are more moles of oxygen than calcium carbonate sway you. We've already seen that if you have a lighter thing, it could weigh less. So even a fraction of the mass of the calcium carbonate, that is oxygen, could actually be more moles. So let's try a harder problem that is going to require us to combine together a few of the different skills that we've learned so far. we're being asked to find the mass of carbon in 55.4 grams of C10H14O. The first thing we need to recognize is that only a portion of this mass is going to be due to the carbon. Some of it's going to be due to the hydrogen and the oxygen. So the first thing we need to figure out is what portion of this is carbon. So we're being given a simple bit of information here, 55.4 grams of C10H14O. We're being asked to find a mass of carbon. Our solution map for this is more complicated than ones that we've done so far, and it requires us to first go through the moles. And that is because, as we've seen, we can only figure out, the easiest way for us to figure out what portion of this is due to the carbon is to see that there are 10 moles of carbon for every 1 mole of this. Again, a lot of students will try and figure out some way around it where they go directly from this mass to this mass, and there really isn't any way, okay? The moles are your gateway for doing these kinds of problems. So let's look at our relationships here. First thing we're going to do is we're going to figure out what is the mass of 1 molecule of C10H14. We add them all up and we see it's got 150.2 AMU. Next, we can dump out the relationships that we're going to need. There's 1 mole of C10H14O for every 152 grams. There's 1 mole of carbon for every 12.01 grams. Again, we're getting that from the periodic table. And there's going to be 10 moles of carbon for every 1 mole of C10H14O. We can then plug in all of our different conversion factors, okay? We can see here that this is going to take us from grams to moles. This is going to take us from the moles of C10H14O to the moles of carbon. This is going to take us from the moles of carbon to the grams of carbon. When we string them all together, we can see that we are going to cancel our grams there. We are now in moles of C10H14O. We can cancel those moles. We are now in moles of carbon. We can cancel those moles, and we are now in grams of carbon. And we get a value of 44.3 grams of carbon. We knew that only a portion of this was going to be due to the carbon, so it makes sense that our final answer is less than our initial mass. Let's try one more of those and see if we can find the mass of sodium in 6.2 grams of NaCl. So we're given that we have 6.2 grams of NaCl. We're asked to find how many grams of sodium there are in there. Our solution map looks the same as it did for the other problem. We need to first find the mass of NaCl, that it's 58.44 AMU for every 1 molecule of NaCl. We'll need the same type of statements. We'll need to know how many mass, what the mass is of 1 mole of NaCl. We'll need to know what the mass of 1 mole of sodium is. And we'll need to know the relationship between sodium and NaCl. Now, before, we had 10 moles of carbon for every 1 mole of our C10H14O, okay? Now we have a 1 mole to 1 mole relationship. That does mean that we are going to include this conversion factor, that is 1 mole over 1 mole, okay? Now students sometimes get a little weirded out by this. They don't know what to do during this step when it's 1 mole to 1 mole. They let them throw them off. Or they get into a habit of doing a few of these problems where it's a 1-to-1 ratio and they forget to add this step when we go back and it's not that way. Okay, so I think that it's good to not let it sway you and to still always write it out in each one of the problems you do and make sure that you're canceling those units as you go along. Okay, so we can cancel our grams, we can cancel the moles of NaCl, we'll cancel the moles of sodium, and we see that we get out 2.4 grams of sodium. If we do our check, we can see that this is a portion of this mass, so it works out.